Perfect.
Good
Will you record?
evening.
Okay.
Oh, sorry about that. Good evening, everybody. Welcome to the Triangle Area SQL Server User Group's Advanced DBA meeting for September, second Tuesday of September. And we are happy to have Uwe Richter talk to us about diving into the internals of DML. And I got a sneak preview of what the talk will be like, and it's going to be a good one. So please, Uwe, if you could, take it away.
Okay. Yeah. Thank you, Kevin. So hi to everybody. So I have to say good evening to everybody because it's midnight here in Germany. Quite happy to have a session for the user group, and I hope you like the topic. It's about DML deep dive, data manipulation language, and this session was born when I was doing some consulting services with big companies which had huge problems when they were inserting data into tables, and that was incredibly slow. So then at that time, I was taking a little bit more time to dive deeper into what happens in SQL Server when we insert data, when we update data, or when we delete data. And I was trying to figure out what is the best way to handle these DML operations. And that is one of the points why this session was created by me. A few words about me. Forget about everything what is on the left side. That's only a commercial thing. Most important here is my email address. This session is going to be a level 300 to 400, and I could really understand when some people might think, oh my goodness, this is really hard stuff, and I read it, I hear this, I saw the demos, but I have a few questions. Do not hesitate to send me an email to uwe-ricken@db-berater.de, and I'm quite happy to answer your question whenever it is concerning SQL Server topics. So I'm a Microsoft certified master long time ago. It was 2013, so nearby 10 years ago, and I'm an MVP for the data platform. So this is our agenda for tonight. First of all, we have to talk about internal structures of tables. So what we are dealing with is special pages in a database. We're talking about the difference between a heap and a clustered index, but I promise that's very short. I don't want to go too much into the depth at the beginning. You will see it when it comes to the demos. Furthermore, I'm using lots of functions for investigating the DML operations. So what you will see is functions like fn fils log formatted to see the data page where records are stored. dbcc trace on is quite heavily used in conjunction with dbcc page to look into a data page. And last but not least, the function fndblog, which gives us insight into the transaction log to understand what huge amount of work SQL Server has to do when it comes to manipulation of data. When we were going through the basics, we go immediately, and that's lots of demos, pure only demos. We want to see the inserts into tables with a heap and or a clustered index, an update, same with heap or clustered index. And last but not least, the delete operation. Then I want to give you some tips and tricks how you can speed up the DML operations in the underlying tables. So the special pages in SQL Server you need to understand, and what are quite important for SQL Server are these one here. So you see the PFS page, the page free space. Think about the PFS as a registration office. So in Germany, it's so when you want to relocate to a different city, you have to go to the registration office to say, okay, I'm here and I want to live here. And the only difference between a registration office and a database is the way that when you relocate to a new city, you can settle down wherever you want. That will not happen in SQL Server. So when a new record comes into a table, then the first way what we have to go is we go to the page free space, to the registration office, and we say, hello, I'm here, I want to live here. And then the PFS officer is looking into a list and looking for empty pages and say, okay, you can go into this page, for example. The GAM page, the global allocation map, is something like a road management in your city. The GAM is managing so-called extents. An extent is 8 pages in a row, and these 8 pages are managed in one extent. We can have 2 different types of extents. The first one is a so-called mixed extent, and the second one is a what is it? Oh my goodness, mixed extent and a uniform extent. The difference is very simple to understand. Think about this. Think about the extent as a street. And the special thing with the street is that only 8 houses can be directly at this street. And when these 8 houses at one street belong only to just only one big family, then we have a so-called uniform extent. So that means the whole street belongs completely to this family. And this is exactly the same how SQL Server handled this. When we have 8 data pages which belong to only one table, and these 8 data pages are on this one street, then we have a uniform extent. The different way is that we have the mixed extent, and they get handled by the SGAM, the shared global allocation map. And that is when we have 8 houses at a road, and every single house or multiple houses belonging to different families. SQL Server was dealing with these mixed extent very heavily with SQL Server before it comes to SQL 2016. Maybe a few of you remember that we had trace flags to avoid these kind of mixed extents. That was the trace flag 1118. Since SQL Server 2016, SQL Server is only working with extended events. So the reason for this is coming from the past when storage was really expensive. So at that time, when SQL Server has been used, when storage was expensive, Microsoft was thinking about how can we manage storage efficiently, and that was that they said, okay, as long as a table has less than 8 data pages, then we put the data on different pages in different extents, as long as we have filled up 8 pages. When the 8th page is full and the 9th come into the game, then SQL Server assigned a complete uniform extent to the table. The good thing with working with uniform extents is that SQL Server does not have to go every single time back to the PFS and ask for a new page, because then we knew that these 8 pages belong to or were reserved for this one table. Last but not least, we have the IAM page, the index allocation map. And this is something like a land registry entry. The IAM page is used for every table and every single index. So every index, in the same way as every table, has its own IAM. And this is important when we read data, especially when we read data from heaps, or when we read data with the option with no log or read uncommitted. In this case, we need the IAM page because SQL Server must know, hey, I want to read this index, or I want to read this table, and the IAM page has a complete list of all pages which belong to the table and or the index. We will come later on to this, especially to the PFS page. The PFS page is one of the problematic pages, especially when it comes to heaps. The biggest problem with the PFS page is that when we store data in heaps, then SQL Server will record the so-called filling level of the data page. Think about this. A page can hold 8,060 bytes of data. The rest is overhead for management of the page. So when the first record comes into a heap and it allocates a page, then SQL Server automatically say, well, this page is filled by 50%. So whether you have only 1 byte stored or you have 4,000 bytes stored, SQL Server will always think, come on, it is half full. And this can definitely lead to problems when you have a wrong, or let's say a not so optimal data structure. I will come later on to this. So we have 5 levels of it. The 0, the page is empty, and 100% it's full. And in between, we have 3 more different levels: 50%, 80%, 95%. Attendees were mostly asking, hey, why is Microsoft using these numbers? To be honest, I don't know. That's a decision by Microsoft, and that has been in SQL 2000, it has been in SQL 7.0, and it is in SQL 2022. It's exactly the same. They never changed it so far. So the functions, what I'm using, what you see in the demos is the fuzlog formatter. It gets information about the logical location of a record, and I'm using fndblog to have a look into the transaction log. So the function fndblog should be used very carefully because, so as every speaker will tell you, do not use this in production. The reason is that when you run fndblog, then it scans the transaction log file. And as long as this scanning is going on, the log clearing for the transaction log is disabled. So that means that your transaction log will not get truncated for a backup, or if it's in simple recovery model. So keep that in mind. So these are functions what I'm using in the demos. And now I think that we can walk through the differences. Here are DBCC page. That's okay. You will see too, because I want to look with you together on a data page to understand how SQL Server is storing the data. So when it comes to DML, you first of all need to think about what type of table you want to use. Do you want to use a heap, or do you want to use a clustered index? And a heap is a table without a clustered index. The clustered index is exactly the same. It's a table, but then it is ordered by an order key. The heap table can have 1 or more non-clustered indexes. That's not a problem because they can be created on tables. And the key point, what makes heaps so interesting, is that data is stored in a heap without a specific order. And this is something where I have mostly very heavy discussions with others, because I'm a fan of heap, because heaps can store data incredibly fast. Because the data get not stored by a specific order, so that SQL Server need to control, hey, I have to put this record exactly on this page, or I have to move it to this page, and so on. Think about a heap like a puzzle game. So you have a puzzle with 1,000 pieces, and a heap is the puzzle with the single pieces of the puzzle completely unordered in a box. So that is how a heap is working. The good thing with a heap is when you think about this puzzle, you can take all the pieces of the puzzle and throw it immediately into the box. You don't have to take care about any order. So put the pieces and throw them directly in the box. Don't take care of where they get stored. And that makes storing data in a heap incredibly fast. Maybe you are working with data warehouses and you have ETL processes to load your data warehouse. The staging area is mostly heap tables, because you can store very quickly a huge amount of data into heaps. Usually, data is initially stored in the order in which the rows are inserted, but there is no guarantee for this. The database engine can move the data around in the heap to store the rows more efficiently. And one of the things of the heap is that a data order cannot be predicted because they get thrown into the table as they are coming in. The clustered index is completely different. The clustered index is the table. So the clustered index is formally the heap. And the difference here is that in a clustered index, the data gets stored by a key attribute. For example, an ID or a name or something like this. So when data are coming into a clustered index, then SQL Server must store the data in the order of the primary key or of the clustered key. Yeah. And this is the only way, really the only way to store data in an ordered form. The problem with the clustered index, what I see as a problem is that a table which is a clustered index is bigger than a heap because a clustered index must have a so-called B tree structure. You see it here from the root node, intermediate node, and so on. So when we store data, when it comes to the DML operations, a clustered index might have a little penalty of time when it comes to storing data, because then when we insert new data into a clustered index, SQL Server must go through the B tree to find the correct position where the data must be stored. And this is something what we do not have in a heap. Yeah. So long story short, heap is the table in an unordered way for the data, while the clustered index is the table but ordered by the index key. So now we come to the DML operations. So let's start with insert. So let's say we have created our table and now we want to insert data into it. The first question what we have is it better to have a heap or is it better to have a clustered index? So what I want to demonstrate here, what is the best way to store efficiently the data in a heap or in the clustered index? It does not come to selecting data. It's only, keep it in mind, we want to insert data really fast. A heap is an unsorted bunch of data, that's clear. And an insert command into a heap has a little drawback, which a clustered index does not have. An insert command is, first of all, going to the PFS page and asking for a page where it can store the data, and then the PFS is scanning and say, well, okay, you can have the page number X, because that belongs to the table, and I see that it's only filled by 50%, for example. And then at that time, when we know the page, then the data can be stored. In a clustered index, we don't need it. In a clustered index, we don't need the PFS, because when we insert a record into a clustered index, then we have one decision what we know, and this is the index key. So the value of the index key. The value of the index key determines at what position the data must be stored. So it checks the free space, not on the PFS page, but on the data page itself. So let's do a little demo to understand this. So I have restored my customer orders. This is a demo table, a demo database. And we go first of all to the anatomy of a heap. So what I'm doing here is I create my database called DemoDB, and then I create a heap table. So heap does mean that we do not have any clustered index on it. So here we have the ID and 3 different columns. And I insert now 1,000 rows into this heap table. Okay, so the data are in, and now we want to see how SQL Server will organize these data. And by the way, I'm working here with SQL 2019, so think about this. We do not have mixed extents here. And what we see is we have stored 1,000 rows, and these 1,000 rows are stored on 70 data pages. What concerns a little bit is this here. You see that we have the data pages and used pages, and they have different values. The reason is these 1,000 rows are stored in these 70 data pages, but every table and every index must have an IAM page, at least one. We have a small table here. So the 71 does mean that we have 70 data pages plus one IAM page makes in total 71 used pages. Another thing, what is quite interesting is this one here, the total pages. And the total pages is here 73. And this value, 73, does mean that we have one IAM page. So the rest is 72. And now think about this. SQL Server is managing data pages in extents. One extent has 8 pages. So when we divide the 72 by 8, then you see that we have here 9 extents. The good thing here is when we see the 72 and compare it to the 70, we know that we have 8 completely filled extents, and the last extent, only 6 pages are filled, while 2 other pages are empty. They are not used yet. So when we insert more data, then these 2 pages get filled the same way. Next thing, keep in mind we are in a heap. What you see here in this heap is that we do not have any root page. A root page can only be available in a B tree structure. A heap is not a B tree, and a heap has only an IAM page, index allocation map, and then we come directly with the data. So there is no tree above that which we have to follow to find a record. But we see here that we have an IAM page. This is the number 120. And let's have a look into the number 120. And what we see then is very interesting. So here we are, and we go to this. This is the interesting thing. So whenever SQL Server is reading data from a heap, the first thing, what then happens is when the select starts, so when we grab the data, the first stop is at the IAM page. And the IAM page has 2 different methods to store data. The first one is the so-called single page allocation. The single page allocation means we have 8 data pages which can be stored in mixed extents. You remember, a mixed extent is a street with 8 houses, and these 8 houses belong to different tables. In our table here, we can say, well, that is cool. We do not have houses or data pages which are on mixed extents. And every single time when we have this feature activated, that we can use only uniform extent, the reading is a little bit faster because the first 8 pages, SQL Server does not have to jump around the storage to say, take this page, and this page. And here it comes to the uniform extents, and what we see here is the following. From page number 1 to page number 8095, these pages do not belong to my table. They are not allocated. This not allocated is always referencing the objects of the table. But what I can say here is that from page 8096 to page 8167, these pages belong to my table. And this is exactly the 72 data pages. So then I clear it, and we can go now to the clustered index. Now let's see the difference between the heap and the clustered index. And with the clustered index, here comes the very important information. When you're dealing with, or when you create clustered indexes, then you have to be very careful how you define your clustered index. Let me show this here for you. Again, I create a demo database, and then I put 1.6 million rows into this table, 1.6 million rows. These are customers from my big database, what I'm using when I'm talking about column store indexes and so on. And what I'm doing now, and notice this, is that I create a clustered index on the table, which is non-unique. And believe me, I see it very, very, very often when I see the table definition and I have a look to the clustered index, and then I see that it has been created like this. Create clustered index, name of the index on the table, and the ordering attribute is the attribute c_key. What does this mean? Now, when I start this statement, I let it run here. So now what SQL Server is doing, it takes the heap data and transferred it in an ordered way to a new destination and recreate the table, but now it is ordered by the c_key. So now we have a look to the page allocation, and now you will see a very interesting thing. We have 1.6 million rows, and see how much space it is using. We are here consuming around about 290 megabytes, and we have 36,560 data pages. As I said, data pages. That means only for data. And here we have the used pages and the total pages. The used pages is a little bit higher, and this is because of two special things. I go back to the slide deck. The first thing what a clustered index have is a B tree. The B tree is calculated as a data page in SQL Server. So that is one of the reasons why we have so much more use pages, plus the IAM page. And another thing what we see here is that because we have a root node, that we have a balance tree, sorry, then we must have a root page. A root page does always mean the top node of my index. So whenever SQL Server is looking for data, or we want to look for data, SQL Server must start always in the root node. And from the root node, we go into the next level, and into the next level, and into the next level. So let's see how the root page is looking like. So here we go for this. And again, I'm using DBCC page to have a look into the page, and keep in mind that I have excuse me, a look into the root page. And what's quite interesting here is the root page, or every index page, is, or here the index key. You see the C custom key. This is my key attribute. And now think about this. When I have created my index, my clustered index, I didn't tell SQL Server that it must be unique. But a clustered index always must be unique. So what is SQL Server doing? When we do not handle it as a unique index, then SQL Server will take care of it. And this is the only type of index where SQL Server is taking care of it, because it must always be unique. And you see this funny thing here called uniqueifier. We don't have this column in our table. SQL Server will automatically create for every single record a separate, not visible column, let's call it uniqueifier, and stores a unique number that the combination of the cust key and the uniqueifier, these both together, that these are guarantee that the record is unique. The problem with the uniqueifier is it consumes storage. And this is always, whether it's used or not, it's an integer. That means we have 4 bytes plus on every single record, only because our index is not unique. So this is the very first customer key with this uniqueifier on this page. So when it comes to a select on a dedicated customer number, then SQL Server is going into the root level, is looking for the customer key. Let's say we are looking for 30,000, then SQL Server knows the 30,000 must be between 20,931. And this year, this number is the lowest number on this page. So SQL Server now, for 100%, identify that it has to go into this child page to go down to the leaves. I do this. This is my second IO. So here we are. So you see, this is the very first value, and it goes down and down and down and down. And again, we have a uniqueifier, 4 bytes. Always keep that in mind. We are consuming here 4 bytes, to be honest, for nothing. Absolutely nothing. Yeah. So when I look for this number, I have to go into this page. I do so. And here we will find the records. So now we are in the leaf level, and I want to show you the problem with the uniqueifier. You see here, this is my record. You see the customer number, the market segment, the nation key, the name of the customer, and so on and so on. But we have a uniqueifier on top of it for this record. And not only for this record, we have it for all. I guarantee you this is for all. And look to this. The length, also, it's not filled. So the 0 does mean for SQL Server, well, I don't need it. I don't need to fill in a 0. It does mean it's empty, but it is an integer, and an integer is a fixed length data type. So that does mean that SQL Server is preserving 4 bytes for maybe another value, 4 bytes. So we have 1.6 million rows, and keep in mind that we now have 1.6 million multiplied with 4 additional bytes, which are completely useless for us. And now it comes to the problem when we insert data, we need to insert the uniqueifier on top of it. So when you have extreme heavy workloads, and I have this demo for this, for really heavy workloads, and it comes to store data very quickly, and every millisecond counts, then, to be honest, I don't want to have a uniqueifier, which is useless for me, but important for SQL Server, only for the reason that I have not defined my clustered index as unique. So whenever it comes to a point where you say, my natural key is not unique, make sure that you then use a surrogate key, which you define as a clustered index if you want to have a clustered index. So see how it works. So statistics IO and time on. I want to see how long it takes and how much IO it takes. And the good thing with an index is that whatever index key you're looking for, the access path is always the same. So I'm looking for this one, and you can see here that we have 4 IOs. So root level, intermediate level, it goes down to the leaf level then. So 1, 2, 3. The reason why it is 4 here is that SQL Server is not sure, hey, is on the next page another value, for, another customer with the same ID. When it is on one page only, when it's sure that it's only on one page, then look to this. Then we have these 3 IOs here. That's absolutely brilliant. So whatever key you're looking for, SQL Server is going always the same access path. Okay, then I clear it. So we skip the non-clustered index because a non-clustered index is nearby the same, but before we go to the inserts, to the DML operations, I do a little change here. You see, I've created my clustered index. Let's have a look again to the number of consumed pages. 36,560. Now I create a unique clustered index, and that does mean that SQL Server does not need the unifier because the index key itself, what? 1 second. So with drop existing. 1 second. Okay, and now. So now we will see what's going on now. Have a look to this. So we have 5 megabytes less because we have way less data pages, and that's very, very easy to understand. We do not have the unifier, so 4 bytes less for every record, 1.6 million records, and that's it. Let's have a look only to the root page to understand this, what is going on here. Unfortunately, I always have to change the numbers because there is no predictable number where the records get stored. Have a look to this. You see that here the unifier is missing. So that means that SQL Server definitely knows that this number can only be once in the table, and we do not need to have a helper column which guarantees that this record is unique. Hope you understand this. So 4 bytes less. And when you're dealing with clustered indexes, I can strongly recommend to make sure that you always use a unique clustered index for a better performance and for less storage. So I go for this, I drop this. Okay. Yes. Okay. So now I skip the non-clustered index. That's not interesting. Let's go now directly into the DMLs. So first of all, I insert rows into a heap table. Again, keep in mind that a heap table has one big problem. A heap table can store data only when it knows in which data page is enough space to store the data. Therefore, SQL Server must always have a look or have to ask the PFS page to say, hey, where is the next free house from my table where I can lay me down? So I create a table, demo table, and you see here, this is the ID, column 1, so 400 bytes, 404, the date time, and an insert position. So that's it. So the table has now been created, and now let's have a look to the pages. So you see, also we have created the table, no data pages are allocated. So, and no transaction log, checkpoint, sorry, must clear the log. Yeah, there is nothing in the log, and now we can start. So here we come. I started transaction because when I don't do this, it's quite difficult to understand or to see what SQL Server is inside the engine. I started transaction called insert record, and now I insert my very first row into the table. And what you will see here is the inside of the transaction log, so the DMTran log, what has been locked here. So you see a data page and you see a RIT. The RIT is the so-called row locator ID. And this belongs to the demo table. This here is internals because now SQL Server creates the table physically in the database. It will always be created in the moment when the first record gets in. And you see that SQL Server is hold on the table itself an intent exclusive log. That means, hey, I want to store data in the next level. So that means I hold only an intent exclusive that gives other processes maybe the chance to select data while we are writing. Intent exclusive. I want to. Then in the hierarchy, from the object, we go down into the page, the data page. You see here, this is my data page, 8096. And we hold on the page an intent exclusive log, say, I want to save a record on the page, but I don't want to keep the complete page locked that nobody can access it. And then we store the record itself. This holds an exclusive log because while we are storing this record, nobody can read it. Now I commit this. Here we are. And then I'm looking where SQL Server has stored the data. See that I'm using the physlog cracker, and I see that my data are now stored on this page 8096. And now see what SQL Server was doing step by step. And this is really interesting. Now I'm taking a look into the transaction log. And in the transaction log, I now see exactly step by step what SQL Server was doing, what different steps SQL Server had to do to store one single record. Let's go through it and see what it was doing. It's very easy to understand, step by step. Think about this. You are new in town. You go, first of all, to the administration, say, my name is Uwe, I want to live here. So the first thing what then happens is that a new extent gets created, a street which is for you. Next thing then is, and this is something what is really interesting here, we have to go to the PFS, to the registration office. But what we see here is, oops, it was happening very, very often. You see here 1, 2, 3 times. And the reason for this is not only data records have to go to the PFS and say, hey, I want to store data here. But what we have, first of all, before we can have any house in the city, we have to go to the IAM. We must have an IAM which document that this house belongs to my table. So what we are doing here is we're going to the PFS and asking, sir, excuse me, I need to have an IAM page. So the PFS then is looking, hey, where is a free page? Oh, yeah, you can take this one. Then we go again to the PFS and say, I want to insert some data, want to have another a data page, which is data page. And then the PFS goes again and looking where is a free page, which I can hand over. The third one, we forget this about here. This is from internals, which is not so important for us. But look now, when we were coming from the PFS, we have a document which guarantees us, well, the page number 1 and the page number 2 belong to my table. At that moment, when we have it documented, we create our pages. The first page, whatever we need before we build any house, is our IAM page. So you see, now SQL Server creates my IAM page, and then it sets a bit. And not only one bit. What the first entry in my IAM page is my very first house, what belongs to me. It means that it say, well, the page number 2, this is the page which belongs to you. Okay, now build the house. Here we go. Yeah, the format page does always mean build the house. And when the house is finished, what you will do the same way is you will move into the house. Insert row. And this is again into the demo table here. Yeah, so now we are going into the house. My record is moving into the house. And now comes the problem of the heaps. Oh, a possible problem of the heaps. Because now the status, the filling status of the data page has changed. Before we were moving into the house was empty. And now the very first record comes in, and this will cause automatically, I go back to this here, and the page filling level changes from empty to whatever value. We have to go back to the PFS and say, dear PFS, I'm now living in the house, and now my house is 50% filled. So this can lead to big problems when you're dealing with heaps, especially when it comes to hundreds of thousands of parallel inserts into a heap table. Because every single time when the filling grade is changing from 0 to 50, from 50 to 80, from 80 to 95, from 95 to 100, we have to go to the PFS page and record this. So this happens here too. My page is empty. I go into the page. Now the filling level has changed from 0 to 50. I go back to the PFS and say, my house is now filled by 50%. And the officer there is just only marking the table, say, thank you, sir. Now live well in our great city here. Let's check this. I want to see my data pages, which are now belonging to me. Remember this. In SQL Server, since SQL 2016, SQL Server tries not to use mixed extents. So this is the reason why you get immediately 8 pages in a row. And all these 8 pages are recorded in your IAM page. The good thing here is the 8096 belongs to you, but not only this one, the next, the next, the next, the next, and so on. They all belong to this table. The good thing here is that we now don't have to go again to the SCAM page, because it's only for mixed extents, and say, hello, this house belongs to me too. And that makes inserting activities way faster, around about 20% faster than permanently go into the SCAM page while my table is so small. So here's my data page. And this is the 8096. Let's have a look to the PFS, what it will say about this page, 8096. I go into the registration office, and here are all my houses. This is the list from the officer. Be very quiet, because he gets annoyed when you see that you're looking at his list. 8,096. I scroll down, 8,096. 1 second. What's going on here? Oh. Am I blind? No, once again. I don't know what page. I'm in demo. Oh, this is live. Then 1 second. Do it this way. And you see it here. So here you can see this is coming from the PFS. It tells me this data page, the page free space percent. So how much percent do we have free? It tells me, well, it's 50% what on data what you can put on this data page. Now I'll do a little math. The problem here is that we only filled 400 bytes. I demonstrate this to you, 896. Go into this page. Here is my data page. And the interesting thing for us is this one here. You see this? This is the free count. The free count on the page itself tells me how much bytes do we have to store data. So now we have a discrepancy between what the PFS knows and what is on the page itself. So the PFS thinks, well, we can store 4,030 more bytes. But the page itself tell me, well, I have 7,800 bytes for free. And this could lead to big problems, which I come later on. So now we drop this table and we create another one. And here comes a point where what you always, really always should be very careful with. When you create tables, think about the data structure very, very well. Think about it before you insert data into this. Here is the problem. I create a table, a heap table. And what you see here from the heap table is that I store the ID, which is 4 bytes, and another column, which is only for filling data, which consumes 2,500 bytes. So in total, we have, we can store 4 rows into 3 rows in one data page. Here it is. Here's the calculation. The page size is 8 kilobytes. The header, the slot array, not important for us now. And here's my data. This is my workload. So we have 8,060 bytes. One record, when I store it on this table, has a size, a full size of 2,510 bytes. 4 plus 2,500 and the row header and so on. In total, it does mean when we have 8,096 and we divide it by the length of one record, it is absolutely clear that we can store 3 records on one page. Let's try it. I start my transaction and see what I'm doing. This is slightly different from what I will do next. I insert 3 rows within one single batch. So 3 rows are coming directly into the table. Go for this. And you can see now that SQL Server will here permanently fill the data. So we have here, one moment, here, insert row, insert row, insert row. And that's always in the same data page. But, you see this? Go to the PFS, go to the PFS, go to the PFS. What happens here? This is the bottleneck of a heap. Definitely a bottleneck of the heap. Because every single time when we insert a row, then SQL Server might change the filling level. I go back to my slide deck to understand this. The first record comes in, 2,500 bytes. So the page was empty, and now it gets filled up to 50%. Okay, we just only have 30%, but it doesn't matter. The PFS must know, oh my goodness, it's 50% full. So first row comes in, 2,500 bytes, 50% full. Second row comes in, 5,000 bytes. 5,000 is more than 50%. Update again, 80%. The third row is coming in, and then it seems, well, sorry, it is now nearby 95% full, and we need again an update. So these are the three updates of the PFS. This is, or this can be, a big problem called PFS contention. You might see PFS contention mostly on TempDB, but it can happen on heap tables in your database the same way. But here, all my data are now stored in one data page. It's in page 232. So flush the changes. Okay, you have seen that when we insert multiple rows within one batch, then SQL Server can handle it very perfectly and could put the data on one data page. But every single time, and that depends on the size of your record, it might be that SQL Server must permanently update the PFS page. And bang, then you got the contention. Now, I'm doing it in a very different way. Look to this. I start my transaction again. Now see what I'm doing. I do not insert the 3 rows in one batch, but I'm doing it in 3 batches. And now you will see a disaster here in a heap. The first one is my oldest daughter, then my oldest cat, and then the second cat. Yeah, we have cats. So 3 rows are inserted, and now I commit my my actions and have a look to this. You will see a different scenario here. We go step by step. The first thing is the new records cannot be stored on the format page, the 232, so we must create a new page. Here, the PFS, we go to the PFS and say, oh my goodness, the house number 232, it is full. Please give me a new house. And the PFS is looking and looking and looking and saying, well, you can have the number 233, for example. Then we build this house, and Katarina is going into the house. I hope so far everything is clear. Due to the fact that the house was empty at that time, and now Katarina was going into the house, she has to go back to the PFS and say, hello, officer, now the house is filled by 50%. The PFS is recording this, and the transaction or the batch is gone. Now, Emma is coming into the house. Again, 2,500 bytes. So now we are hitting the limit of 50%. That does mean when Emma is going into the house, she again has to go to the PFS page and say, now the house is more than 50% full. And what the officer at the PFS is doing, say, it's noticed, well, thank you very much, ma'am. And now it is 80% filled. 80%. And now, suddenly, we come again to the PFS and see this, and this is some weird thing. Suddenly, when the third one is coming, we build a new house. What's going on here? So we know that with the first transaction, we had 3 rows which were completely in one data page. But now when the third is coming in, SQL Server creates a new data page. Oh my goodness, that is some weird thing. And then the third one is getting into the house and has again go to the PFS and say, now it is 50% full. The reason is, unfortunately, the design of the table. We go through this. First of all, let's see that we have 3 data pages. This is from the first transaction, Uwe, Bea, Alicia. And then Katerina was getting into a new house and Emma was getting into a new house, but Josie is in a third house. So we have a completely different behavior from what we have seen previously. What is the reason? The reason is, let me see this. You see that is number 233 and 234. Yeah. Okay, so let's have a look to the PFS. We go and complain the officer of the PFS. 200 and, come on, 230. Was it? 1 second. Oh my goodness. I forgot the numbers. So it's 233, 233, 233. Here. 233. Ooh, you see this? SQL servers say, well, it's 80% full. This is from Katarina and Emma, and that's correct. It's 5,000 bytes. And then Josie was going into this page, which is now, because only 1 record is in, is only 50% filled. And what happened here? This is a little math. The problem here is how SQL Server is looking for space in pages in a heap. We concentrate on this number, the number 230 or 33. You see that it's well, it's 80% free. Let's do a little math. When we say a page can hold 8,060 bytes, and we say that it is 80% filled, what does this mean? It does mean that we have 8060 bytes multiplied with 0.8. And what is this? Roundabout, because I don't have the real number, it's 6,400 bytes. So when I have 6,400 bytes and I subtract them from 8060, and it's 6,400, what will be the rest? The rest is 1,660 bytes. This is the problem. So we have the PFS thinks that we have only 1,660 bytes free. And now comes Josie, which say, sir, I'm 2,500 bytes in size. And what will the PFS then do? The PFS will say, oh, sorry, you do not fit into this page. You get a new one. And this is the problem only by design of the table. So that makes it very complicated. So when you insert row by row by row, always in separate batches, in a heap table, it could lead to a heavy fragmentation, or let's say not really a fragmentation. Heaps cannot be fragmented, but in unused space on a data page. So when you're thinking about using a heap, then make sure that you first, before you decide for a heap, make sure that your data or that your structure will not lead to these big problems. Use heaps when you have small records. But if you have big records, then think about twice. And then I would recommend clustered indexes instead of heaps. So I clean the kitchen, and that's it. If you have any questions, feel free to ask, and Kevin will hopefully forward it to me. Let's see what a insert in a clustered index will cause. So this is a little bit different. Notice this, and this is the big difference. When you insert data into a heap, you might or you can be the victim of the PFS page, because before you insert a row into a heap table, you always have to ask the PFS, hey, where is space for me? In a clustered index, you will never ever have this situation, because a clustered index will not go to the PFS page. The PFS page is only for allocating new pages, but it will never ever ask a PFS, hey, can you tell me on what page I have to go? A record which gets inserted into a clustered index will always follow the B tree structure down to the leaf level where it has to store the data. So I create my demo table again, and the only difference here, it's exactly the same. The only difference is that I now have a clustered index on it on the ID. I start again, it's exactly the same. I start my transaction and I insert my very first row. So what SQL Server is doing now, because it's the very first row, it creates the table. And here you don't see, and that's a big difference, you don't see a writ row locator ID, but you now see a key. A key is always an indexed attribute. Yeah, never a heap. Heap is always a writ, and any kind of index will always have a key block. Let's see what SQL Server was doing here, and you see immediately the difference. Here it is always again, it's the same. So we create our street, then we register our IAM and our first page in the PFS. This is internal thing. Then we create our IAM. We record our first house in our IAM. We create our house, and here comes the difference. We insert our row, but we do not go to the PFS page to record the filling level of my page. It is not necessary in a clustered index. As I said, only heaps where we store the data wherever some place is requires the PFS, but a clustered index do not. A clustered index forces the storage of the records in the order of the clustered index key. So now you see here that our data are stored in this data page 8096. The slot is 0, so that was the first one. I do a checkpoint. Now I insert number 5. I commit this transaction immediately, so the 5 is the clustered key, and here, see this, only this. We do not go to the PFS to update it again. We only go directly into the clustered index, store the data, and that's it. And when we store data on a data page of a clustered index, the free space on the data page gets recorded on the page, but not on the PFS. Here are data. And you can see now, Katerina is now first. This is a logical order. Keep that in mind. It's not the physical one. So Katerina has now, it's because it's number 5, it is now on the first position, and then it comes me. So SQL Server orders the data. What was the page? 8096. Yeah. We don't have to do this. I don't go into the page. I drop this. Try again the same example as we had with the heap with this big table. So with the big records. So I create again my table, and you see again the 2,500 bytes, but now I have on the ID a clustered index. Doesn't matter whether it's a primary key or it's a unique clustered index here. Checkpoint. So here's our calculation again, and let's see what happens. I insert Uwe, Bea, and Alicia, and as expected, SQL Server will automatically put in the data all on one data page, all on 2 132. Now we do it again with the 3 separate ones. And the difference here is, because we do not need the PFS page, SQL Server must follow the B tree structure, and whether we are putting it in with one batch, 3 rows in one batch, or every single row in a dedicated batch, it doesn't matter. SQL Server is checking the free space directly on the page. And that is the reason why we can easily store now all 3 rows on one separate data page. And that is the big benefit of a clustered index here. So I hope you understand that whether to choose a clustered index or a heap is not only depending on good recommendations from blogs or from videos, but it's depending on data structure and what you really want to achieve. Want you insert very quick? Do you have a good database design, very small records? Then maybe a heap is the better choice. If not, if you have big data here, so big records, then it might be definitely better to have a clustered index on it. I, to be honest, do not follow the generic recommendation from Microsoft, hey, every table needs to have a clustered index. There are definitely, really definitely points where I say, no, a heap is the better choice. And I will show it to you. So this was the insert in a table, the difference between a heap and between a clustered index. The next thing is, how does an update work? With updates, we can run into, again, problems with heaps, but the same way with clustered indexes. An update in a heap may allocate the existing space if the record will have enough space on the page. So we go to the PFS, say, hey, is there enough place? The PFS says, yeah, you can go to this. And then it could be on a page, which is not the very last. It could be wherever it is. But if an update will increase the max available amount of data on the data page, then you can run into problems. And these problems are expensive. It's called forwarding record. A forward record will be generated when SQL Server must move a record from one page in a heap to a different one. Updates in a clustered index will have the same problem, but there it is called page splits, and they are quite expensive the same way, because then a page split does mean that not only this one single row goes to a new page, the row what we update, but half of the data on the page. So when you update in a heap, only this single record, the transaction volume of the move of this single record gets recorded. So if the record is, let's say, 200 bytes, then your lock is only 8,000 and a little bit more, let's say 8,600 bytes. While when you're updating a clustered index and it's moving half of the data page to a different data page, you have over 16,000 bytes in your transaction log. You might say, oh, come on, 8,000 bytes or 16,000 bytes. What the difference? Think about availability groups. Think about availability groups with a long distance in between. So you have one server in Seattle and you have another one in Singapore. And you're transferring your transaction log over the wire. And that could definitely lead to big problems. So we want to have our transactions as small as possible. Writing in a transaction log might be incredibly fast, but do not force it to say, what are your limits, log? Yeah? Try to keep transactions very small. Let's see how it works. So update in a heap. I create my demo database. Here we go. Create again my demo table, and then I insert 50 rows in it. So these are single transactions. Every single time, insert row, insert row, insert row. And now my data are located here. You see, it is on the page 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so on. And you can see that we have lots of data stored, 31. So 31 data are now stored on this page 8096. When you have heap tables, or you decide your data structure should use heaps, make sure that most of your columns are fixed length columns. Do not, so it's recommended, do not use varchar. Better is to use fixed length like char or nchar. But if you change, or if you do updates, you see here the column number 1, it's a char 200. So whether we are storing only a few data, we always reserve 200 bytes for it. And the column 2 is a varchar 200, variable length. So what I'm doing now is I begin my transaction, and then I do an update on a fixed length column in a heap. The good thing here is that we now do not create any new pages. So we get an in-place update. SQL Server is the only database which is doing in-place updates. So you see, this is my record, and this record is now, or actually because we're in transaction, is now in an update phase. Let's have a look to the transaction volume, transaction amount. So my transaction log bytes, what I'm using here is 296 bytes. These 296 bytes are coming from the text, this one here. This is longer than the sum stuff, so a few more characters get replaced. And so 296 bytes get used. I commit my transaction. Here is my transaction log. And what you see here is we are modifying a record, in a heap. And what you see here is the old data and the new data. So this is my transaction, what it was previously. So this is for an undo, and this is for a redo. So the new data, I take these both data. Now I make it visible for you what it was. So, and you see here, the sum stuff gets replaced by, this is a brand new text. And the rest of it was filled with spaces, and SQL Server will not take this into account to change it again to a space. So when there are characters which are exactly the same situation as it was before, then it gets not recorded, not changed. Checkpoint. So now I'm changing the column number 1. I have to have a look again. Sorry for this. It's a fixed length. So, all right, I think I can skip this because this is okay. Commit transaction. Okay, so, oh, sorry. Live. So, but what happens if we do something like this, so that I say this is a brand new text, and so on? What will SQL Server do when we do update a column multiple times? I start my transaction, do the first one. You see that it's always the same record. This is a brand new text, and so on. And let's see what SQL Server now is blocking. It's always only one row. This is a good thing. And the interesting thing is, what is the total amount of transaction log? 504. That does mean that SQL Server will insert for every single update a separate transaction log entry. So this is the first record in the log, this. Then it comes to is, and then it comes to a brand new text for me. And this causes 3 records in the log. So when you must update records, and believe me, this is not only because I had an idea to demonstrate something, I saw this in applications. I saw exactly this in application that they say, okay, first I put this in, then I gathering some more data, and then I update it again. Then I'm gathering some more data, and I update it again, all in one transaction. This is absolutely a mess to do that. Collect the data, and then do the update. Here it is. Yeah, this is the first old data, then this one, and this one. And this is something what we really do not want to have. So checkpoint and clean the kitchen. So this is a normal update when you do an update in a heap on a fixed length column. But now we come to the biggest problem we have. It's called forwarded records. So look to this. I create a demo table and I put in 2 records. Have a look to the structure. You see that the column 2 is a varchar, variable length 8,000. So then I was pushing 2 records into the table, each one 3,500 bytes plus 4. That's okay. So 3,500 bytes. So that means all are fitting to 1 page. Perfect. 3,500 bytes. I do a checkpoint. And now, 1 second, it was 8,096. Have a look to the PFS, because we are here in a heap, 8,096. What the heck is going on? I don't see it. However, not so important. I start a transaction. Now comes a very, very funny thing. What I'm doing is very simple. I take the column, the record number 1, and I expand from 3,500 to 5,000. So in total, we have 8,500 bytes. And to be honest, you all know this cannot fit to 1 data page. Okay, let's see what happens. Update. And now see this. Bang. 16,000 bytes transaction log for only 1 single update. The reason is not only that we replay 3,500 characters by 5,000 characters, but now we have a big overhead for the creation of a new data page. Let's see this. Here we go to the PFS, because SQL Server now knows, oh my goodness, we need to update a record. Now it goes to 5,000 bytes. It does not fit on the page. Hey, PFS, I need a new house. So the PFS say, okay, you can take it. We build the house. We insert the row. But the curious things here is, what we are doing is, oh my goodness, it's only 3,620 bytes. Oh my goodness. What happens here? What SQL Server is doing, this is really curious, it does not replace the 3,500 bytes by the 5,000 bytes. No, it copies the old record to the new house. This is the 3,600 bytes. So then this house, or the filling level of this house, has changed. So what we have to do, we have to go back to the PFS and say, this new house is filled by 50%. Okay, very cool. Then we modify the row. That means from the 3,500 bytes, we expand it to 5,000 bytes, but that means replace the 3,500 by 5,000 new characters. 3,500 plus 5,000 is 8,500 and a small overhead. In that moment, when we expand it to 5,000, we are hitting the new threshold. We are now going from 50% filling level up to 80%. Shit, we have to go again to the PFS page, say, oh, sorry, the record was grown up. It's now not even more a baby, it's 18 years old. And now we are consuming 80% of the house. Thank you, said the PFS. That's fine, no problem, don't worry. But on the other hand, there is another thing what happens. Think about this situation here. We moved or we copied the old record to the new page. But then when this one was finished, we delete the old record, or not, no, we do not delete, we change the old original place where the record was before. We made a change on that record, which consumed 3,624 bytes. You will see later on what was the change. And due to the fact then previously we had 7,000 bytes in total on this page, now we were shrinking the record size from 3,500, I can tell you, to 10 bytes. And then the filling level of the former page where the record was has changed again from 80 to 50. So this one goes again to the PFS and say, sorry, now my partner has left me, so I have 50% free, not only 80. And look to this, how often we were changing or we were hitting the PFS 4 times. 4 times in one transaction. And now think this, what will happen if 100 processes will permanently update rows in a heap? You will definitely suffer from PFS contention. So then it is not a good idea to have a heap in it. Checkpoint, clear the log. So now it really gets funny. Set statistics IO on. What I want to measure now with this primitive select, give me all the rows, is I want to see how many data pages I read. Well, what must be the situation? We have 2 records. I show it to you here. And these 2 records are now, curious, isn't it? And this is some strange thing. You remember I made an update on the row number 1, but SQL Server is telling me, well, it's on the same page. However, what we have is we must have 2 pages, definitely 2 pages. The first one is where the second row is, and the second page which has been created with this transaction. So what I would expect here is I need to read 2 data pages. 1, 2, and look to this, and this is weird. 3? What the heck is going on here? We have 2 records, each record on a separate data page. So we can only have 2 data pages. But why is SQL Server reading 3 data pages here? Think big. Don't think about, oh, we have only 2 records. Think about you have 2 million records. And now think that 10% of these 2 million records are so-called forwarded records. The point is, that SQL Server is reading a heap in a so-called allocation unit scan. And the allocation unit scan does mean that SQL Server reads the IAM page and follows the structure of the IAM. And we're doing it here in slow motion. First step. Let's see, first of all, this one here. You see this? This is my IAM page. This is my first data page. And this is the second one. I tell you that on this page, there is the record with the number C, or with the ID 2, I promise. And on this one, we have the record with the ID number 1. And you see it here from the page 3%. The first one, where we just only have the smaller row with 3,500 bytes, it is consuming 50%. The second one is consuming 5,000 bytes. So 5,000 bytes is more than 50, it's 80. So therefore 20 is free. And what I'm doing now is I'm going to the IAM page. And here comes the point. When you read a heap table, think about a postman which was drunken yesterday night, and now in the very early morning, he needs to deliver the letters. And this is the way how he is doing this. First step, he comes to the post office and he takes a look to the IAM page because he needs to know the route to go. On the IAM page, he will see here, oh yeah, I have to go to the house number 8096. It only shows the first value of the extent, up to the house number 8103, because these are allocated by the table. This is the information what the postman has now in his mind. Go to page number 8096, 8097, and so on, and so on, and so on. Good. We do it. We start with 8096. And now comes the big problem of the postman. The postman is following rules. And the rule is what the IAM said. The IAM said go from 8096 till up to the end. So we start in 8096. And now he is going to the first house, and then he see, one second, then he see this here. And now he is standing in front of the house saying, I have a letter for Uwe. And there is a small note on it say, Uwe is not living here. Uwe has relocated to house number 8097. And now the postman is doing a very, very crazy thing. Instead of now saying, well, okay, now I'm at the house number 8096, then I deliver this one here. No, it does not. So it comes to this point and say, oh, I have to go to this page. Then he goes to this page, read the data from this page. Here it is. This is the AAAA. He has read the page, and what is he doing then? He say, oh, I have to go back to this one and read the second one. So we were going to 8096. There is a forward information. Please come to 8097 and deliver the letter there. Then he goes to the 8097 and comes back to the 96 to read the rest of the page. But this is not the key point. The biggest problem comes now. So we were now reading two pages, going back to the beginning, reading the rest, and now he follows the rule of the IAM again. Because let's say you have to go to page 8097. And what does it mean? It goes now again to the 8097 and read nothing, because there is only the forwarded record. And this is the 3 rows what we have here. I have it I have a picture for this, and it's looking like this. This is exactly the same situation. The postman is coming to the IAM and you say, well, I need to read 119, 121, and so on and so on. Then it starts reading data. It comes to the page number 119. In 119, the first record say, oh, I'm not living here. Please deliver to 156. Step number 2. SQL Server will move over to 196 and read the record, number 1. When it has read this record, it goes back to the 119. And then it starts reading, oh yeah, the IAM said go to 119, to 121, 126, and so on and so on. And then comes the really, really stupid thing. The postman did not recognize that he has been in 196 and goes 156 and goes again to 156. So, and this is the problem, the page number 156 will be read 2 times. Or in other words, a forwarded record will always read a data page twice. What the heck is going on? So forwarded records are incredibly expensive based on the access path on the storage, because it needs to jump on the storage. Okay, SSDs or flash is not a big problem, but I would say try to avoid this. Try to avoid forwarded records. But as long as you have variable length attributes, you cannot avoid it, because when you update it and it gets larger, then you automatically will create forwarded records. So this is the problem we have with heaps. Yeah, and this is something what we always need to take into consideration. So then I will clean the kitchen. In a clustered index, it will work a little bit different. I don't want to show the demo here because I have a more interesting demo here. This is more a quiz for you. What happens in a clustered index? Instead of forwarding records, you will have page splits. The problem with page splits is that the transaction lock amount is bigger, or can be bigger, than it is in a heap. So when you see this here in the first line, you see that the orders are all well organized. So the index has been rebuilt. So the orders 1 to 50 are on one page. Then we go over to the next, and all are pretty good in line. So we can read the orders from left to right, no problem. In the moment when we do an update on one of the records in one of these data pages, and the update will not fit on the page, what will happen then? You see it here in the second depiction. So I made an update on the order number 37, and then SQL Server will move half of the orders from the very first page at the very, very end of the index. So we create a new data page, and we move 4,000 bytes over to the very last data page. And then we update the references to the different pages and see what happens here. It's exactly the same as what we have with forwarded records. We read the records from the orders from 1 to 36. Then it stops. We go to the end of the table, read 37 to 50, and then we go back to the orders. The only difference between a heap and a clustered index is that in a clustered index, a data page will not be read twice. That is the difference. But all the other drawbacks of splits of forward records are exactly the same here. So my recommendation is, especially when it comes to updates, try to avoid variable length, or if the best would be to have fixed length characters. I always try to do this. It's so funny, you know, when I see sometimes data structures where the zip code, which is, for example, in Germany, it is always 5 characters. What I see then is that people are taking a varchar 20 for this. This is nonsense. Now, we do not have variable length, so why not take a char 5 if we know that our data which we are storing are only for Germany or only have 5 characters? And if it have less, don't worry, then we have some spaces in it. But we do not run into problems when it comes to updates on this attribute. Yeah, this is what I would recommend here. I see my voice is going. So what I see is that we have, let's say, another 10 minutes. I want to jump over to a different thing. I skipped the delete. There is not very interesting thing. I want to really come to this one because I promised you that I want to show you that you will be astonished when you see the results of it. And this is coming from a real world scenario. I was working for a chemistry company which were producing drugs, and also pills and tubes and all this kind. And what they have to do is, this is by German law, every single charge must run through a quality check. And this quality check was happening on 24 let's say quality machines. So they were scanned, they were checking the weight and all this kind of stuff, and they permanently writing data into one database, into one table, into a log table. And they were having big problems because let's say at the late afternoon they saw that the write queue from the web service which were grabbing the data was filled, and that the insert statements were not as quick as the new data were coming. So we analyzed the system and we came to a conclusion to change the structure of the table. And we had 3 options. The first one is, and this is a recommendation, what I see in blogs, what I see in videos, or on YouTube. I see it nearby everywhere. Whenever I read something about heap clustered index, I would say over 95% see the recommendation. Every table must have a clustered index, and it must be straightforward, only growing values, and so on and so on. The first one will cover these recommendations. I will now create a clustered index with an identity. So 1, 2, 3, 4, and so on. The next one will be a clustered index with a GUID. Whenever I talk with developers over GUIDs, they are shuddering and say, my goodness, no, this is bad, this is evil, don't use it in SQL Server databases. Nobody recommends to use GUIDs. And the third option was a heap. So unfortunately, we are not doing an in-person event here. So normally I would ask you, what do you think? Who will win this race? Is it the clustered index with an identity? Is it the clustered index with a GUID? Or is it a heap? And I want to prove it by evidence that it is not the most recommended clustered index for SQL Server. It will not be the number 1, the clustered index with identity. I go very slowly, step by step through it to demonstrate to you how this will work. Here comes the demo. First step, I create my demo database, and then I create 3 different tables. Here's the first table. The first table is the recommendation, what you will always read in books, in blogs, and so on. I have an ID, which is an identity, so it's permanently growing, 1, 2, 3, and so on. And I have a char 400. This is only for the payload. And you see here that I will have a primary key on the ID. So this is a clustered index. Second table, this is the GUID table. It looks exactly the same. The only difference here is, excuse me, I take a unique identifier, and what you see here is that the column 1 is smaller than this one. The reason is a unique identifier will consume 16 bytes, but an integer will consume 4 bytes. So this difference, because I want to have exactly the same data record length, so I reduce it by 12, and that makes 388. Go. And the last one. And the last one is the heap. The heap, so no indexes. I have an ID. I fill it with an identity, and I have my column 1 with 400. The good thing here is, and that was before 2012 a nightmare, the identity gets cached, so this will not be taken into account, this few milliseconds of grabbing a new identity value. Then I create a wrapper stored procedure. It's called proc insert data. What I'm doing is I have a variable called type, which defines in which table I want to write the data, and the number of records. So when I say, please type in the numeric, then we put into the numeric table. When I type in the GUID, then in the GUID, and otherwise in the heap. Perfect. Now I'm taking a tool called ostress. The ostress tool is from Microsoft. It's part of the RML utilities. I strongly recommend for you, when you are a developer, to use it to simulate workloads. And that can prove the concept of your database. Does it work with hundreds of thousands of headings of your databases? And what you see here is I start my ostress here. This is only the first one. I copy this and I go into a command box and paste it. Let me explain to you what this one will do. So I start ostress. I go with Windows authentication into my server instance 2019, and I execute this stored procedure, what I have created from before. I first start with the numeric table and I insert, that's unfortunately you cannot see it very clear, but you will see that I insert 20,000 rows into it. And I do this with 24 processes simultaneously. I have an 8-core machine, so that means that we have at least always 3. So 8 can work at the same time, so 16 will wait. I put it into the database DemoDB, and I do it in a quiet mode. So silently, I don't want to see the results here. Before I start this, I do some preparations. First step, I clear my weight stats because I want to see for every single test what was the most massive weight type this process was waiting for. Then I take this query and I will execute it while the ostress tool is running to see what is currently going on. And I'm counting the number of processes which are waiting for something. So now I start this. Again, 24 cores, 24 processes are now inserting every single process 20,000 rows into the numeric table. The clustered key is on the ID, which is an identity. Ready, steady, go. So now while it is running, see this. Have a look to the resource where we're waiting, for what we are waiting, and look to the number of sessions who are waiting here. And look to this. This is the wait type, pagelet X. That does mean that they are fighting for an exclusive access to this resource. Oh, it's done. Oh, that was quick. I inserted 480,000 rows in less than 15 seconds. Oh, yeah. So lots of people will say, well, that's good value. That's perfect. That's, here say, clustered index on identity. It took 14.5 seconds. We analyzed this. I want to see what are the primary weights here for this site. And this, to be honest, this is a disaster. This is a pure disaster. Think about this. Pagelet X does mean that we were waiting to get access to a row where, or to a space where we want to insert our rows. And in total, for the whole process, we were waiting for more than 50% of the whole workload only to get access to the data page. And in average, it took me 0.2 milliseconds. This is a really, really bad picture, a really bad picture. And 23% for the shared log, pagelet shared log. So we want to select something. And on the third position with 20% only is for writing the really, really, really most important weight, the write log. And the moment we write data into the log, it gets hardened and the transaction can be finished. But you see here that we were waiting only 20% of the whole time was waiting for write log. In other words, it does mean the system was more heavily in use with waiting for exclusive logs and shared logs instead of writing data. And this makes it slow. Slow, slow, slow. The log is acting very well. We are waiting when we were writing less than 0.1 milliseconds. This is because I have a flash disk here on my system. Okay, we reset the weights. Mark this because that goes very quick now. And now let's do the very, very ugly, very evil GUIDs. GUID. Ready, steady, go. So I go back and see what's waiting. Look to this. Is that, oh, finished. Let's see this. Cool. The same workload, really, I do not cheat here. The same workload. But this was only 3.5 seconds. Wow. Now we come to the heap. The heap, we all know that a heap will have a drawback, but before we go to the heap, let's see what SQL Server was primarily waiting for. Look at this. This is what I want to see. The pagelet X is so incredible slow. It's really nothing. SQL Server was permanently writing data This is a perfect picture for a heavy workload when we write data. We want to have most weights in these kind of processes, or we want to have the most time only waiting for write log, but very, very short waits. This is because of the good storage here. So what this picture shows me here is, yeah, we were writing lots of data and SQL Server were never ever, you see, less than 1%. SQL Server never ever had to wait for resources. SQL Server was permanently writing data. And this is a very good picture for this. Very cool. And now we come to the last, the heap. I reset this. We know that the heap will have a small drawback, and the problem with the heap is always the PFS. Let's see how the heap is now working. Let's check it. Wait stats cleared. I mark. I want to see what is SQL Server waiting for. Absolutely nothing. I go back and ready, steady, go. And so now see what SQL Server is doing. Oh yeah. Oh. This is not so good. You see this? SQL Server has exclusive logs and lots of resources are waiting on this. And now I think it's finished. Yeah. So, but heaps, although we have drawbacks with the PFS, are very, very fast. What is the problem here? The heap will suffering from its permanently updating PFS page. So that means when we have 24 processes permanently writing data on a page, we are going permanently up and down to the PFS and record, hey, we have 50%, hey, we have 80%, hey, we have 95%. Now it is full, give me a new, and everything goes over the PFS page. So the PFS is here the bottleneck. The PFS page is the hot point here, the hot spot, which is causing the heap to slow a little bit down. But against all discredibility, let's say, against heaps, GUIDs, the GUID is performing the best. But now developers are coming with this statement. Well, yes, I know that the GUID might be better, but when I use the identity, I do not have index fragmentation. This is a common scenario. This is a common statement. What I hear very, very often. Let's check it. You will be surprised. What you will see here is, this is the query. One moment. Yeah. So what I'm doing is I'm doing it with a union all. You see, I want to have the fragmentation of the numeric table, of the GUID table, and the heap, all three together. Have a look to the numeric table. Bang. We have a fragmentation of nearby 30%. And when I show this to developers, they are really, 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 really surprised. Absolutely surprised. And again, another point is, look to this. The page counts here with the heap, with the clustered index on the identity, and the GUID table. The GUID table has way less pages consumed. This is really interesting. And the heap table, okay, a heap table cannot be fragmented. Forget about the fragment count. This is nonsense. A heap can never be fragmented. Have again another look to the average space used. So that means for how many percent in average are my my data page is filled. And this is really, really interesting. So the clustered index has an average filling of nearby 60%, while the GUID is 10% more. So we have 66 to 70%. And the best is the heap. Okay. But now we can come to a very simple single conclusion. What we can say here is the fastest one, and you will never beat this, is the GUID table. The second fastest is the heap, but the GUID table, from my point of view, is, depending on the speed and the average space used, my favorite. One drawback is the really, really heavy fragmentation. It's 99%, and that does mean that nearby every single page does not go from this page directly to the next one, which is directly next to this page. So we have lots of fragments here. But this is a typical thing, what we have for GUID tables. From my point of view, from all around the world, recommended solution is the baddest. And let me explain why, and you will understand it when you see this. So we can say the clustered index with the GUID is the fastest, and I would, with heavy workloads, strongly recommend to use the GUID version. Why? Look to this. The problem with the identity is the so-called hotspot in a clustered index on an identity. What will happen with this one? Think about this. There are 24 processes are coming. Everyone holds an ID. I have the ID 1, the next one with the 2, the 3, the 4, the 5, and so on. And when we have a clustered index on an identity, so an ever-increasing value, all my rows will be inserted on the very, very last data page. So that means, think about this, that 24 processes are permanently here on this page. Say, I want to insert. No, I want to insert. Everybody wants to insert here till the next page will come. And then the crowd is going to the next page and try to fill this. And every single time, 24 processes are waiting. And you have seen these waits. That was the page/X. The page/X on the very first demo was coming exactly from this last page contention. And this is the biggest problem we have with this so-called permanently increasing values. When it comes to big workloads, it cannot scale. And the biggest problem here is you can do absolutely nothing against this. Even because when you talk with data warehouse engineers, what will they recommend to you? They will tell you, well, distribute the data over multiple data files. This does not work because this one single page is on one database file. So no chance to scale here. The hotspot is the problem for the time. But what is the problem for the fragmentation? The fragmentation problem is this here. The identity values, when they get inserted, every single process will get, oh, excuse me, my voice is slowly going down. Every single process which wants to insert has, first of all, to grab an identity value. And that works very well. You see this here. So you see this one had the number 1, number 5, and so on and so on. The problem is that the processes who wants to insert the data will not come exactly in that order as they have grabbed their identity value. You see it here. The first one now inserts the number 7. The next one is the 11 that will fit. But then For whatever reasons, the next one in the queue is the number 4. And now you see where the fragmentation is coming from. So when the number 7 and the number 11 will fill the data page, it's completely full. And now the number 4 is coming. What will happen? We will now start the page split. So that means that the half of the records will go to the end of the index before the number 4 and the number 2 can be inserted. And we have the first fragmentation. And that happened here thousands of times. With a GUID, we definitely know that we have this situation, because when we have random GUIDs, we cannot predict on what data page the GUIDs get stored. But look to this. When we come with 24 processes, everyone has a different GUID. It's a random GUID. I don't take care about the fragmentation. It doesn't matter. It's not important for me here, because we do not do range scans. We want to insert data fast. But then the 24 processes gets evenly distributed over all data pages. So we do not have a hotspot in the clustered index, but we can distribute the data when we have 24 and we have, let's say, 24 different leaf pages. Then it could be that all 24 processes will write into a different page. And that makes it so incredibly fast, because we can work or we can write simultaneously. And this is something what we cannot do with the identity. So how can we speed up heaps? And this is the last point. When you have, for example, timeline databases, something like this, where you have sensors which are pushing data permanently into a table, and you decide for a heap, you can get rid of the PFS contention in a very simple way. And I believe that you all know how to work out this, because you always doing this. What you're doing is to scale your SQL Server is a very simple thing. What you are doing is, I can show it here. When I go into the tempdb, here is the solution. We distribute the workload over multiple files. And that is exactly the same what you should do with your database. So if you have a database where you have heavy write activity, and with lots of processes writing data in your table, in a heap table, as I say, in a heap table, distribute your heap table over different files, because every single file will have its own PFS structure. And that makes it fast. So I would say, but this is a guessing game here, yeah? So I have to read my crystal ball. But I would bet that when my database would not have just only one database file, but let's say 4 or better 8, I would bet that the heap would be near the clustered index on the GUID. I would estimate around 4.0, 3.9, 4.0, a second less. So this is more an architecture than a developer problem, but therefore you will have your experts to handle this, to do or to write, to build properly databases. I really, really hope that you enjoyed the session. For me, it is 2 o'clock in the night, 2:10, but it was worth every single second to demonstrate to you how fantastic it is, how you can improve write statements on your databases. Do you have any more questions?
If there are any questions, chat, now is your opportunity for it. No questions in here so far, although there was a comment that there is a lot of useful information in here, and I wanted to concur that this has been an outstanding presentation.
Thank you so much. I really enjoyed it. And I hope that you all enjoyed it the same way. So if anybody of you will be in Seattle at the PASS Summit, just come to me, say hello. I would really appreciate it. And yeah, if there's no question, Kevin, then I would say a big thank you to all of you, to the all of the audience, and I wish you a pleasant evening. For me, it is time now to go to bed.
Fair enough. It is rather late. So with that, thank you again so much, Uwe. We appreciate all the time that you took this evening, and hopefully we will be able to see you in Seattle.
Yeah.
At least anybody in chat who's gone to Summit. But with that, let's wrap things up for the evening. Quick reminder, next week we have our main meeting. 1 week from today, then 2 weeks from today, we have the Data Science and Business Intelligence meeting. All of that you can find at meetup.com/tripass, TRIPASS. And until we see each other again, everyone, take care.